Okay, so welcome to the next topic in IB chemistry, atomic structure. As a New Zealander, I'm pretty excited about this because we talk about Rutherford a lot. Okay, so it's going to be broken down into three parts. So the first part, which is today's lesson, is the nuclear atom. The second part will be the electron configuration and ideas around there. And finally, the third part will be electrons in atoms. So the nuclear atom. By the end of this, unit of this topic, you should know that atoms contain positively charged dense nucleus composed of protons and neutrons. Protons and neutrons collectively are known as nucleons. Negatively charged electrons occupy the space outside the nucleus, and that the mass spectrometer is used to determine the relative atomic mass of an element from its isotopic composition. You should also be able to use the nuclear symbol notation we see here to deduce the number of protons, neutrons, and electrons in atoms and ions, and calculate non-integer relative atomic masses and abundances for isotopes given data from your data booklet, including mass spectra as part of that data. Okay, so let's now look at some atomic structure, some basic atomic structure. So atoms, you should know, are very small, about 10 to the minus 10 meters or 10 nanometers. All atoms are made up of three subatomic particles: protons, neutrons, and electrons. So pause the video now and see if you can label the following diagram with protons, neutrons, and electrons. Okay, so you should have labeled this guy the electron, kind of hanging out by himself in the orbital. We'll call that guy the proton, or girl, and we'll call that guy the neutron. Okay, so protons and neutrons form a positively charged nucleus, this thing in the middle, and the electrons are in energy levels outside the nucleus. And those energy levels are illustrated by the orbits, as you will. Well, that's kind of the model you've had anyway, so we'll go with that for the moment. Right. So subatomic particles. The actual values of the masses and charges of the subatomic particles are actually in your data booklet. So you can see that a proton is quite massive compared to an electron. Okay, about 1,000 times bigger, is it? Yeah, about, well, even 10,000 times bigger. Okay, so the mass of an atom essentially is in the proton and in the neutron. Okay. Also, the charges are also based around the proton, which is positive charge, and electrons, which are negatively charged. So the relative way to think of it is through relative masses. So the electron is about 4,000 times smaller than a proton or a neutron, as you can see from the table at the bottom of the slide. So this is the notation that we use. You have element X in the middle, and we have Z, which is the atomic number, and which is known as the number of protons in the nucleus of the atom. It defines what the element is, also known as the proton number. Okay, and the number of protons in an atom will always equal the number of electrons, because atoms are neutrally charged. The mass number A is the sum of all the numbers of protons and the number of neutrons in the nucleus of an atom. Okay, some periodic tables have Z above A, but remember A will always be the biggest number. Okay, so let's see if we can use this notation. Okay, so calculate number of protons and neutrons in chlorine 35. So pause the video now and see if you get the right answer. Okay, so you should have found out that Z is the number of protons, which is equal to 17. That's the lowest number there. Okay, which means that the number of electrons must be 17 electrons, and the atomic mass is going to be 35. So it's going to be number of protons and neutrons. So to work out number of neutrons, it's simply 35 minus 17, which gives you 18 neutrons. So hopefully you all got that correct. Okay, isotopes though. So isotopes are atoms with the same element but with different atomic numbers, because you've got different numbers of neutrons. Chlorine's a prime example. Okay, so different mass numbers, one's chlorine 35, one chlorine 37. Okay, because chlorine 35 has 18 neutrons, whereas chlorine 37 has 20 neutrons. Okay, they're isotopes of each other, chlorine isotopes. And they're usually referred to as chlorine 35 and chlorine 37. Here's some isotopes of carbon for you, carbon-14 and carbon-12. Carbon-12, the most common isotope. 99% of all the isotopes on Earth are carbon-12. Has 6 protons and 6 neutrons, atomic mass of 12. Whereas the carbon-14, which is used mainly for radiocarbon dating, has 8 neutrons and 6 protons. So it's 2 more neutrons than the carbon-12 isotope. And isotopes have pretty much the same chemical properties because they have the same number of electrons, and electrons determine the chemical properties of an element. However, isotopes have slightly different physical properties because they have different numbers of neutrons. Okay, so isotopes of an element with fewer neutrons will have lower masses, obviously, faster rates of diffusions because of their lower masses, lower densities because, again, of their lower masses, and lower melting points and boiling points. Also important for isotopes is the fact they can be used for radioisotope work, okay, in medicine, because they have unstable nuclei and therefore emit radiation. They can also be used to detect gas leaks, be involved in, again, medicine through radiotherapy and chemotherapy, used as medical tracers in terms of iodine, especially for thyroid cancers, nuclear power, and they can also contaminate the environment and give us poisoning through radiation. So there's the good and the bad of radioisotopes. So some industrial uses can be used to detect blockages in underground pipes. So a radioactive isotope, which is a gas, can be passed down a pipe, and then you can detect where there's high concentrations of the isotope forming with a Geiger counter on the surface, and that's where your leak in your pipe's going to be. Okay, it can also be used for quality control. So it basically will determine how thick your paper is, for example, because radioactive sources only have a certain penetration. Okay, so if your Geiger counter cannot pick up the radioactive source, it means your paper is getting too thick. Or if your Geiger counter is having an increased amount of radiation, it means your paper is too thin, in this particular example anyway. Radiotherapy, very important. So for example, this cobalt-60 source is being rotated around the patient and focused on a tumor. So the healthy surrounding tumor receives a smaller dose, so it actually ends up destroying the tumor, in theory. And radiation, very radioactive, very dangerous. And also iodine, as I mentioned, about thyroid cancer. You can actually treat thyroid cancer with iodine because iodine is absorbed by the thyroid. So if you treat your patient with some iodine 131, the radioisotope, it's going to be absorbed by the thyroid and attack the cancer in the thyroid. Mass spectrometry is also important. So this is the diagram here. So in the diagram you can see when charged particles pass through a magnetic field, they will be deflected by the magnetic field, bit of physics there. And the amount of deflection will be dependent on both the charge of the particle and also the mass. Okay, the more massive it is, the less deflection there is, but the higher the charge, the more deflection there is. So highly charged small particles get deflected the most. So you can actually use the mass chromatogram, which you get out of the mass spectrometer, to determine the relative mass. Okay, so here is boron being put through the ringer here. Okay, so 81.3% has a mass of 10 and 18.7% has a mass of 11. So can you work it out what the mass of the boron atom is from the following spectrograph? Pause the video now and let's see if we can get an answer. Okay, so you can see from the chromatogram that the MZ value of 11 is an 18.7% abundance and the MZ value of 10 is an 81.3% abundance. Now we know that the charge on boron is +1, so these correspond to the mass values. With that information in hand, we can state that that would be mass 1 and mass 2. Then the relative atomic mass of boron is going to be the atomic mass unit of 1, which is 11. times its percentage abundance, 18.7, plus the atomic mass unit of 2, which is 10, times its percentage abundance, which is 81.3, divided by the total, which is 100. So plugging those numbers in, we get 205.7 plus 813, and which is 1018.7 divided by 100, which is 10.2, which is going to be your answer. Okay, so final example here. A mass spec chart for a sample of neon shows it contains 90.9% 20 neon, or neon 20, 0.17% 21 neon, and 8.93% 22 neon. Calculate the relative atomic mass of neon. Okay, so pause the video now. Make sure you can work that out. Okay, so welcome back. So just with the previous calculation, this time working with 3 different isotopes, plugging the numbers in, you're going to get 90.9 times 20, okay, 90.9 times 20, 0.17 times 21, and 8.93 times 22, divided all over 100, which will give you 1818 plus 3.57 plus 196.46, divided by 100, 2018.03, divided by 100, so 20.18. So that's how you can use a mass chromatogram result to work out the atomic mass of a relative atomic mass of a element from the corresponding isotopes and fragmentation pattern.